don't know that a comment, it's really the count of the number of clients referring to that component. Okay. And server locks is it doesn't have anything to do with the state of the component. It's a way for a client to say, I want this thing to stay in memory, even though this DLL will stay in memory, even though you think it ought to be, even though the count, even though the component count and the reference count are 0, I want it to stay in memory anyway because this is a high traffic application and I don't want to keep shutting it down, starting it up, shutting it down, starting it up. So GC server locks is just a way to hold it in memory, even though everything else tells COM to unload it. Friendly name of component. So compiled programs like we're running today use GUIDs, but scripts can't compile in GUID definitions. Doesn't have a way to do it. So scripts use names. They're not as reliable. You know, you can have two components with the same friendly name. There's nothing that prevents that from happening. GUIDs, Microsoft went to great lengths to try to make them absolutely universally different. Okay. The GUID, part of the GUID definition has to do with your machine parameters. Part of the GUID definition has to do with the date, you know, stuff like that. So, the friendly name and the version program ID are things that the scripts would use, but we don't. We can, but we don't need to. Program ID. So there's, and now I'm going to do some output, and so I've defined at 41 a constant wide string component with some tabs. I'm just going to say, let me run it and you'll see what's going on. When you build it, if it's not built with ATL, if it's one of my raw examples, you need to compile the IDL first. And then you compile the component. And then you register the component, and you won't find, I'm going to show you how to put this stuff on your menu and use it. So I just registered, I put information in the registry about this component, and we'll come back and talk about that after we're done looking at the code. And now I'm just going to run the client. Oh, yes. So I forgot to start my Visual Studio up as administrator, and so these calls will fail because Microsoft's attitude is, if you're not an administrator, you can't start a service. So let me shut this down and then start up as administrator. And now we'll run it. And now we'll run it. Come on. Let me re-register the component. So startup. Oops, and now tools, register comp. Yeah, you got to make the client start up. Yeah. Okay. So all of this was a long way to say at line 41, I'm just doing this, just for the display. That's all. I'm trying to tell you what is the that's mine. It's not yours. Okay. I may have another one. Let me see if you have them in there, dig them out.
Same one which we had day before yesterday. Right?
So I'm looking at what we had yesterday. Yeah. So you take my stuff, I don't have anything to talk about. So what I'm doing, I'm saying, here's the client is doing this, the component is doing this. I'm trying to make that obvious. Okay, and we'll go back and talk to it after we've looked at the code. So now here comes the definition of the component. So this is the class inside the component. So if we look at is anybody, I have one extra copy. Is anybody, yeah, you're missing, so let me get you. I don't think I have the diagram, so for the diagrams you have to look on. But, so in this class diagram, what CA is just this guy, right here. It's the core, it's the guy that's implementing our component's functionality. I think that mic is too loud. Let's turn the mic down. Way too loud. Okay. Okay, so that's what we're beginning to define, and I'm deriving from iString. Okay. Now that, notice that I pound include component.h. Until I ran the IDL compiler, that didn't exist. So at line 14, I'm pound including, so I'm still at the first page of component.cpp. At line 14, I'm including component.h, and that was generated by MIDL. Because the header information, what the developer provides is the IDL, and then the MIDL compiler it generates those header files. So if you forget to compile IDL and you build a program, you'll get all kinds of build errors that say this isn't defined, that isn't defined, this other thing isn't defined, because MIDL is defining them. So class CA public iString, and now I have query interface add ref and release at line 53, 54, and 55. Those are the implementations of the IUnknown functions. So I'm deriving from IUnknown, I'm deriving from iString, and iString derives from IUnknown, and we have to implement all those functions. At 57 and 58, these are the two functions that I want to call, that I want to use. This is my custom application, this wonderful application that sends a string and gets a string back. High technology. And again, remember that when I send a string, so these strings are COM strings, beasters. They're really Visual Basic strings that COM adopted as fundamental. Okay, so the first one, the decoration says that this is just an input parameter. In the IDL, we had to decorate it with in, or we wouldn't get the behavior we expected necessarily. Here, this is just a reminder that this is an in parameter. So this is just a little maintenance thing, helping the maintenance program, that's all. It doesn't do anything as far as the compile goes. Obviously, it's a comment. FY, I am returning a pointer to a B string, and what I'm doing, because the server, the DLL, is going to generate that B string, okay? If I passed in a B string, the server has a copy of it, he fixes his copy, I never get it. Because remember, these are really C interfaces. There is no such thing as a C++ reference in COM. You can't have a reference, a C++ reference over. So, you know, where in a normal C++ program, we'd say bster by reference, and then if the server changes it, we'd see the change. Here, this is a C-style interface, so we have to create a location, a value in our client program for that bster, and then we pass in the address of that location, and then COM writes the bster into that location. Okay, and then a default constructor and default and default constructor and a destructor, and you can only I can have a parameterized constructor here, but I can't. There's no way for COM to you know, COM really expects it to be a default constructor. Okay, so, and now at line 63 is my reference count. So here is a count of my use of this object, and I, you know, I may have several pointers to this object in different places in my program. So let's keep track of that for me. Now the destructor, I'm just displaying that what I'm doing. You know, WC out is preface. That's the server. Component constructor, and I say interlocked increment of GC components. GC components is being manipulated by every client, and so we got to lock it. Even though this is a single-threaded department, so we say, hey, we don't have to worry about threading. In our component, we don't have to worry about threading, but in our server, we do, because multiple clients are interacting with that server, and so we do an interlocked increment on that components because two servers might be constructing that object at the same time. Okay, and the destructor decrements the GC components. And now here's the IUnknown implementation. So here's query interface. So I'm displaying what I'm doing with the query interface at line 93. Now, if IID equals IID unknown, so query interface is accepting the ID of an interface we want. If I say I want IUnknown, it'll give me a pointer to the IUnknown interface, and that's what we're doing at line 94. If ID equals IUnknown, I am returning a pointer to myself typed as IUnknown. And there's a virtual function pointer table we have to look at. I probably won't get to it until Tuesday, but we'll look at it and I'll show you. Maybe I'll show you on Tuesday. So what happens when I cast a pointer pointing into an interface, all that does is move the pointer up and down. So, you know, if my class is deriving from IUnknown. So in my virtual function pointer table, I have the IUnknown methods, the virtual methods for that interface, and below it I have the methods fx and fy for this class. And so if I casted my pointer to my class, it just moves it down that virtual function pointer table to point to fx, fy. But when I casted IUnknown, it just leaves it up here pointing to IUnknown. Okay, and so what that means is I can use the IUnknown methods, but I can't use fx and fy unless I recast it to. So anyway, I am casting this pointer to I unknown. Otherwise, if IID equals IIDI string, then I cast it to the I string interface, and now that moves the pointer down to point to fx and fy in my virtual function pointer table. Okay. Now, else, I make the pointer null and I return no interface. I don't implement that interface. If I implemented two custom interfaces, I'd have another block with that next custom interface. Okay, so I can get to any interface I want. Just remember my example where I had a primary interface and an interface 1 and interface 2, and we did cross casting. This is exactly what's going on here. Okay.
Professor?
Yeah.
The client will be asking for a particular component, right? So why are we checking for I unknown? Why are we casting
Because
for
COM sometimes asks for I unknown, and occasionally a customer will, a client will too. Okay. It's rare. Usually the client will ask for some specific interface, but a client might ask for I unknown. I unknown, the pointer to I unknown is an ID for the COM object. And so the client might query for I unknown to get that ID to save it away as the ID for that. You know, if he's got several objects, he can use that as a selector for the object I want to talk to. Okay. And I'm displaying some information, reference count, and so on. Here's add ref. Now, this is where we're adding an additional reference to our object. And normally, clients don't call this. Any COM function that returns a pointer calls this, add ref. So when the client calls co-create instance, he doesn't add ref to say, I now have a reference to this object. Co-create instance called add ref and gives him this pointer that's already incremented to 1 or whatever. But when he's done, he has to call release because COM has no way of knowing when he's done with a component. So normally a client won't call add ref, but a client does call release. Any function, whether it's in the COM runtime or your function, if you're returning a pointer from that function, then a COM pointer, then a pointer to a COM interface, then you got to call add ref on that. So add ref, just increment, interlocked increment on that reference count, and release is interlocked decrement on that. And if the count equals 0, then delete this, commits seppuku. Okay. Now I'm going to implement my methods. So hresult standard call FAX. I just display the beaster. So I send it a beaster, and all the server does is display it, and then it returns. And it returns a status SOK. Okay. And now for FY, the server is going to generate a string and pass it back to me, and here's how he does it. So I need to allocate memory on the string for the server. The OLE str takes an ASCII string and turns it into a wide char string. COM internally uses entirely wide string. Okay. And so normally COM clients will use wide strings just because all of the Windows API is really using wide strings, but they go out of their way to hide that from you. They give you two versions of any function in the Windows API. There's an AW, so it's some function A, and there's also a version, some function W. And the some function W just accepts the string and passes it into the API. But if it's an A string, then it converts that A string to a wide string and then hands it to the platform. And the same thing on the reverse. When it's coming out, if it's a W function, it just sends it out, wide string. If it's an A function, it converts it to an ASCII string. So typically you'll see my clients will use wide strings just to avoid that conversion. So now notice I'm saying contents. So contents of BSTR. So I am filling your slot, client, you allocated a space for the BSTR. At line 144, I'm filling that with this message from component. And what I did was I call sysalloc string OLE_STR. So the OLE_STR message from component turns that into a wide string message from component. And now I am allocating the string and initializing that allocated memory with that wide string. And now I say the contents of this pointer is equal to that. So that just writes that out into the clients. But something tricky is going on here. Suppose we are in different apartments. The code is written exactly the same way. But you say, hey, if I'm in two different apartments, here's the client, here's the server, and now the client has this beaster, okay, and the server has defined this beaster and he's writing it into here, but you say, if they're in two different apartments, he can't write directly into that. He's got a stub, he's got a proxy, he's got a proxy and a stub. So this is whatever that string was, yada, yada, yada. So how the heck does that work? And what happens is that because we've compiled the server against the IDL, the server knows how big, the server knows that that's a beaster. So what he does is in the stub, he allocates memory for the beaster, and what he's really doing is he's writing that string into the stubs slot. And this client has a stub. So now the communication channel is just sending these messages, send, the characters or whatever. And the proxy is writing them into here, blip, 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 and filling it up. So if I'm in the same apartment, that server really has a pointer directly to that beaster and is writing into it. But if he's in different apartments, comms silently put a channel in between, and the server's now writing into the stub, and the proxy is taking those messages and writing them into the clients. So what they did, they went to great pains to hide the fact that there may be communication. You write exactly the same code. And when I first started looking at COM, as soon as I learned about apartments, I said, what's going on here? This can't work. It can't possibly work. He doesn't have a direct pointer, but that's what you're saying. So, after a little looking, yeah, that's what's happening, okay? So now, what happens is it turns out that it's the client's responsibility to delete that memory. We'll see, this is a memory allocation policy. And so how can a client delete memory on the server? And the answer is he can't. What the client does, what happens is the server writes into the slot in the stub that beaster. When the beaster is all sent, the stub deletes the beaster, deallocates that memory. And now the client, when the client deallocates that beaster, he's just deallocating his own memory. So all of that foo-for-ah to make it look like there's no difference whether it's in the same apartment or a different apartment. No difference if it's a direct connection or a proxy channel connection. I happen to think that's a mistake. Okay. Causes a lot of confusion. It's doing all this stuff on your behalf, but does that make sense? Arpit? You sure?
Yeah, sure.
Okay. Newberg?
So you meant to say that...
Zemo? Make sense? You sure? Sort of sure. Okay.
So
Yes.
COM takes care of deleting the memory on the server side, right?
Yeah.
So only the client has to handle the memory deletion on his side. That's it.
Yeah, but it looks to the client like he's deleting memory on the server. The code looks exactly like he's deleting. He didn't allocate that memory. The server allocated it, and he's deallocating it. Now, also, even though this is C++, we have to use these alloc and free kinds of mechanisms. You know, we can't use new and delete because the stub is going to deallocate that, and the stub is going to use the COM deallocator. You know, so we'll go over that. You know, a little later on, but
anyway, client is passing the pointer of BSTR to the server side, right? So like client is allocating the memory.
So what's happening is the client passes to his stub, to his proxy, the pointer, and the proxy is holding the pointer to his space. Proxy holds onto that pointer. Doesn't send it to the server, wouldn't mean it, so it wouldn't be of any use to the server at all. The server might be in a different machine or in a different process. Okay. He happens to be, because we're talking about improc, it will be in the same process, but he's not allowed to directly write anything because of, that's what the apartment is all about. The apartment is like it's very, very equivalent to the .NET.
Process?
Hmm?
Is it like a process?
No, it's we used it in the app domain. App domain. Thank you. App domain. Good help. App domain. App domain is that. App domain is that grew out of that. So, very, very apartment is very, very the migration, the underlying infrastructure is different, but the same idea. This apartment moved into the app domain. Okay. And the same thing's, same thing's true. If I do an assert in an app domain, I'm going to kill my process. If I do an assert in a apartment, I'm going to kill my process. It works the same way. It gives you data separation, but it doesn't prevent you.
So if an exception occurs, it will stop the whole process?
There's a COM rule that says thou shalt catch. Any exception that's thrown in your COM object, you must catch in your COM object. If there's any possibility of an exception being thrown in your COM object, you must catch it, because exceptions are not allowed to cross those boundaries. Okay, the only thing because I may want to run, my client may be using MetroWorks compiler, and the DLL was written using Visual Studio. No guarantee that MetroWorks can catch a Visual Studio exception. None at all. Even though it's C++. There's no binary standard for C++. So the mantra is thou shalt not let any exception flow out of a component. You got to make sure you catch them. Okay, so where did I set my... So now I'm implementing those two methods, and now here comes a class factory, and I got to implement it. So again, I have to implement, because my class factory derives from IUnknown, I've got to implement the IUnknown functions, and the class factory functions, there's two of them: create instance and lock server. Create instance is COM calls to create an instance on my object. So I am at line 158 on page 4 of component.cpp. Okay. So you were looking around, thought you looked like you were searching. Okay, good. So the class factory's job is to provide this create instance. So that will construct an instance of the CA object. And lock server just this function lock server just manipulates the lock that we looked at in a minute. You know, here we're so that's the declaration. Here comes the implementation. So query interface, I have to re-implement this query interface. So if IID equals IUnknown or IID equals IID class factory, static cast IFactory, class IFactory to this. So even if COM asks for, COM is the only guy who's going to use this, and he knows what he's getting when he made that call. So so either way, I'm returning a pointer that's cast to iClass factory. And otherwise, I say my pointer is null, and I return my status, my H result is an E underscore no interface. Now, this is the query interface. So now, I reinterpret cast IUnknown to, I'm reinterpreting cast of that pointer to IUnknown and calling addref. So I'm a function, I'm going to return, so I am calling so I am incrementing, so this is my own reference count. So all I did was increment my own reference count. And then standard call addref just increments that reference count. And release decrements it, and if the value is, if the reference count goes to 0, then he deletes it. And here comes the iClass factory implementation. So that was the implementation of the IUnknown part. Here's create instance. So I'm going to talk about aggregation later. Skip over that. Okay. If p unknown outer equal null, return class no aggregation. Don't worry about that. We'll talk about that. That's a complicated little commism, and we'll get to that later. But here's where I, at line 231 is where I actually, my factory is actually going to create an instance of my object, CA. So CA star PA equals new CA. If PA equals null, return E out of memory, but that virtually never happens anymore. Get the requested interface. So now the client in his co-create instance passed an interface that he wants. So now we query the interface on that object. We call query interface for that IID on the object, and that, you know, the status result might be, it might fail, but we would expect it to pass. You know, as long as the, you know, COM didn't get confused about the IAD. And now I release, PA release. I'm calling release on the factory. So that will, as long as some other component wasn't creating an instance at the same time I am, that will destroy the factory. So the factory only stays alive long enough to create an instance of the CA class, my internal class, and then, but if somebody else is using it, the reason we're reference counting on the factory is that some other client might be using that same factory, or some other part of my code might be using the factory to create an instance. Lock server is I am just incrementing a lock count, server lock count, or if I pass in false, it'll decrement the lock count. So and if the COM will not remove, will not unload the library unless the lock count is 0. Yeah.
So if some other client will ask for the CA class object,
Yep.
so class factory will create it, like recreate it.
Yep.
I think.
So each one gets their own. Each client will get their own
C object.
C object.
Okay.
Okay.
I thought they are going to share and they.
Sharing the code, but they're not sharing that state. Okay.
Professor?
Yep.
Can you please go to line number 189?
Line 189. Line 189. Line 189. Yep.
Yeah, here it seems that the address is being implemented both by Iunknown as well as the class factory, right? What happens when
So there's a reference count for the factory and a reference count for the object.
Okay, but when we are reinterpreting the cast over here,
Yep.
so it's actually calling the address of Iunknown implementation, right? I mean,
But so it's, remember that addref is just an instance of that object, and that cast to IUnknown, to tell you the truth, the way it's implemented, that cast didn't need to be made.
Yeah, exactly.
But this is emphasizing that all I'm really doing here is using that IUnknown part of that. Okay, and it really is a cheap it didn't cost virtually anything. It just moved the pointer, from the object up to the top. But so probably saved a couple of microseconds of when you're using the virtual function pointer table. Okay, it's probably why it was done, to save a couple of microseconds. So. It's just saying, don't look for this method through the entire virtual function table. Just look at this part. Okay, so where are we? So now we're at So we've implemented addref and release and create instance. So the factory has created the instance of CA, if it, it could, and then returning a status code. We implemented lock server, and now we have some DLL functions. As a DLL can unload now. And what that does is it looks to see if the component count is 0 and the server locks count is 0. If both of those are 0, it returns SOK saying, COM, if you want to unload, you can unload this. So COM essentially polls those active objects and to see if it can unload their libraries. Just so that a whole bunch of libraries don't stay in memory, until you reboot your machine. Part of lifetime control. DLL get class object is something you provide so that COM can get to the factory. So here, if class ID equals the ID of our component, if it's not equal to our component, then we return that class is not available. Now, otherwise, I'm going to create an instance of the class factory, and that happens at line 301. So DLL get class object created the class factory. I'm at line 301. Okay, we created the class factory, and as long as that succeeds, we call query interface on the IID that the client wanted, and then we release the factory. Now there's a DLL register server that simply calls if you looked at your code, appended to the back, there's a registry.h and registry.cpp. This function at 318 is simply calling a function in that code, register server. Okay, at the very end, I think there should be attached to that register.h and register.cpp. It's calling that. And I'm not going to walk through that. DLL unregister calls a function in that code to unregister it. And DLL main, we're doing virtually nothing here. What I'm doing is I'm assigning, the only thing DLL main is doing here is giving that variable G underscore module that we saw at the very beginning of the program the reference to the DLL if for some reason he wants it. If your code somewhere needs to access something in that DLL, then it's got the handle to do that. Okay. Okay, so that's a COM component. So you might observe that out of 350 lines of code, about 20 of them were used to implement our functionality. Now, you know, most common components are doing something a whole lot more complicated than we're doing here, okay? So the ratio is a lot better, but there's a lot of infrastructure. There is. So now, what happened here when I ran this thing is, you know, we can see client call the co-create instance, create component, get interface I string, and then component. Here is COM calling. So my client didn't call this. COM runtime called DLL get class object that created the class factory, and then he called add ref, and the factory count is now 2. There's a little bit of, you should say, why is it ever 2? There's a little timing problem that can cause the factory to disappear. There's, you know, so. But, and release it went back to 1. Create component in the class factory. Component construction, you know, CA ref count equals 1. Query interface, return pointer to iString in a component. Add ref, because I'm returning the pointer, it's my obligation to add ref. Query interface, I'm releasing on that, you know, why am I getting, I add ref for query interface and then release. I don't remember why this is here. I'd have to sit and walk through it with a debugger. Okay. Here I am releasing the factory. COM has called release on the factory. Its reference count went to 0. Class factory was destroyed. So it created the object and it goes out of existence. And then query interface return pointer to iString. And then CA calls add ref. Anytime you return a pointer, it's your obligation to add ref. And now query interface and release, so that takes the count back to 1. So now the client succeeded getting iString. And now you know, the client's going to call fx and so on. Client calls fy. You can see the allocating memory for beaster here. And down at the end, if I did my job, it's freeing the beaster memory. But you only see that happen on the client side. You don't see it happen on the server side because that's happening in the stub, and I'm not there, you know, I'm not inside the stub putting these enunciations in. So you don't see that. And in fact, here, there is no proxy and stub because they're both in the same apartment. But if they were, you know, you still wouldn't see it because I didn't get inside the stub code and write those annotations. So, so now, again, what we did was here, we constructed the, we defined the IDL, which, would you close that door? Thank you. We constructed the IDL, which defined the string we want derived from IUnknown, and there was an import of some IDL above generated by the COM runtime, or provided by the COM runtime, that defines the IUnknown. We're deriving from that, and we declare this function is going to send a string to the server and returns the status code, and it retrieves the string from the server, and this is an in parameter, this is an out parameter, and these have to be specified in the IDL. In my code, they were commented out in the client, in the server code, they were commented out, but they have to be in the IDL. And then there's definition of the type library and definition of the component itself, and so it has those three GUIDs. And what has to happen is, for me to run this, I have to compile that, and when I compile that, what I'm generating here is component.h. So, you know, there's a lot of ugly stuff in component.h. Part of it is, there's a part of this component.h that with these type defs, if you're running C, it's building a virtual function pointer table, because C doesn't have virtual function pointer tables. But if we're building with C++, it doesn't, okay? But it's defining the iString interface, okay? And, you know, iString defined, type def interface iString as iString, blah, 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 you know. And so, you know, here's if defined C++ and not defined C interface, you know, iString, public IUnknown, public virtual H result, some method call type fx, beaster, you know, it's done as a pure virtual method, H result, standard method call. These decorations are telling the compiler the protocol to use with the stack. COM these days use something called, it's just compressed to standard, it just says standard call. STDCALL, standard call. You'll see standard call, fast call, Pascal, a whole bunch of slight differences in how the stack is set up and broken down. You know, who's responsible for cleaning up the stack? In some places the caller is, in some places the callee is, depending on what the protocol is. And COM, in order to save 14 nanoseconds and 2 bytes of code, you know, did a lot of horseplay here. Okay. But if we looked at component underscore I.C, here's where the GUIDs are defined. So here is pound define, you know, define GUID, define GUID, and you'll see here type def struct IAD, and class ID improc ex1. This is the name for this GUID. This happens to be the component class ID improc underscore ex1. This is the type library component, and this is the interface component. So now your code needs to use IID string. If it uses the type library, it needs to use this. When you call co-create instance, you need to use this. And I have to tell you, COM sometimes plays little games. It doesn't always use exactly this. So you may use, so this is class IID underscore project name. That's the model. So when I'm trying to get COM to create an instance, I would give it that. But you might find that it would return a failure. And you say, okay, now you go here and say, oh yeah, in this case, it fiddled with that, you know, the name was slightly different. Okay, so you occasionally have to look at this component underscore IAD. Now, when you use ATL, you don't have to do any of that. You know, all of this nonsense is because we're working with raw C++. The IDL library was invented to take all of this off your plate, most of this off your plate. But in order to use ATL effectively, you got to know what's going on here, okay? So. All right. So this was generated by MIDL from the IDL, and component.h was generated from the IDL, and now we're just using it. And so when I build the component, I first need to right-click on this and say compile. That generates the MIDL compile. And then I compile this, and now I register it. If I don't register it immediately, I go build the client, I come back, it won't register this. The way you know, Visual Studio does this, if this has just been built or it's a startup project, then when I register the component, it registers this. But if I built something and this is not, if I built the client and this isn't the startup project, then it won't register it correctly. And you'll get an error message. If let's see if I can trigger it. I'm not sure I can, but let's see if I can trigger it. So the client is a startup. So let's first unregister it. Okay, now let's try to register it with the client being startup. And what I expect is that to fail. It didn't, it succeeded. Sorry about that. But a lot of times it will. But if it does, you know, all you have to do is either just rebuild the component or make it a startup project and register it. Now, so you say, hey, I click on tools and I don't see these. How did you get them? What happens here is there's in C:/Windows/System32, there is an executable called regserver32 that registers components. And if you don't figure out how to install it on Visual Studio, then when you've built it, you got to pull up the command prompt and walk to your project directory. You've got to pull up the developer command prompt, walk down to the project directory, and then type in regserver32, the name of your project. But if you put it on, if you install it in Visual Studio, all you got to do is click. And let me show you how you do that. On the, so here I am on the tools. I go down to external tools, and now you'll see that I have register component and unregister component. So let me just delete the register component, and then I will come back and put it back. So now it's not here. So let's install that. So now I say add, new tool, and I can give it any title I want. So let's say register comp. And now command, that wants me to go to Windows, System 32, regserver32.exe, double click, there it is, arguments, target name, that's my project name, and what you would type in on the command line if you were running it, and initial directory, target directory, and now, okay, I'm good to go. And now I can say tools. Before, remember it was on top, but when I deleted it, now it's on the bottom. So now I just ran it, okay? So that just saves you a bunch of navigating around to call regserver32. And you do that, there's several tools, and I think I gave you in the stuff that I handed out to you, there is a add external tools. And it just shows you how to do it. So there's a tool for adding GUIDs. So if I need to generate a GUID, so you know I'm building a COM component, there's 3 GUIDs, I just click on that, and that tool, generate GUID, and it puts it on the clipboard, and so I just go where I need to paste, I paste it in, and I got a GUID. Okay. You should never, let's suppose that you were going to take this component, and I'm going to change the functionality, I'm going to gut the functionality, put the functionality I want, and then use it. But you are evil if you don't change those GUIDs. If you don't change the GUIDs, you will write over the registry the GUIDs to your new component, and now mine won't work anymore because you changed the registry settings. And so I'll get even with you, I'll register mine, and now yours won't work anymore. So it's evil not to put new GUIDs in. Okay, it's your obligation to put three GUIDs. Okay, good. So let's see where we are. Okay, so let's just take a quick reminder of what we got. So, and then we'll move on. So we had this class diagram that said that a COM component derives from IUnknown interface, implements a custom interface, and then implements both of those interfaces in the class that carries out the work for the component. But also you have to implement a class factory that inherits from iClass factory, which in turn inherits from IUnknown, and then you implement the class factory, you implement create instance and lock server. Okay? And you also have to implement in the DLL exports DLL get class object. DLL get class object. And so a class object in ComSpeak is a class factory. Okay? So you write that, and all you say is new CA. But should suppose your CA object needed other objects that it didn't create itself, but it was making reference to other objects, then your class factory would have to create those other objects. There's nothing that says a COM component can only have one class behind it, but it's got to have one class that implements the custom interface, but that might be just a gateway into a bunch of other classes it's using. Perfectly reasonable thing to do. Okay? And then on the class diagram, we see the calls. So in the structure chart, we see the calls. So a client calls co-initialize to create an apartment, apartment threaded model, and then it calls, the client will call co-create instance, and that com then calls co-get class object, which then calls your function DL get class object and creates a class factory. And then uses that class factory to create the instance of the object. And then you use it, and then you eventually call release, and then you call uninitialize, and then the com runtime will do this polling to see if it can remove the library. Okay? Akbar? Make sense? Good. And this activation diagram just makes it clear who's doing what to whom and what the sequence is. So it gives you that flow through, you know, so here's the client starting off calling co-initialize, that sets up an apartment. Then he calls co-create instance, that calls that activates the com runtime, that then goes and looks at the registry. So you had to have registered that component. If you forget to register the component, that call will fail. Co-create instance will fail. Okay, and so then that loads the library, and now the library's main is being called. Then it's just hanging in memory while com does this thing. Com does the get proc address for DLL get class object to get the factory. Remember in the DLL, my explicit load, I loaded the library and then I called get proc address. Com does exactly the same thing. That's why I walked through it. Com does exactly the same thing. Uses that. And then com calls the class factory to create an instance, and when that is all done, he has a pointer typed as the interface that the client asked for, and he returns that to the client. Then the client uses that to talk to the server functions, perhaps through a proxy and stub, maybe not, depending on whether they're in the same apartment or not. Okay, and then eventually it'll call release, and com will take it away. So now you got a pretty good idea of how com does its stuff and how you have to write a com object. Fortunately, we don't have to do all that. You know, we'd never get all those details right. You know, it would be the end of the semester before you got project 1 working, okay, if then. So, because there's just a ton of nitty little details.
So, Professor, for the project 1, so we'll be using ATL?
You're going to use ATL. We haven't talked about it yet. We will. Real soon now, okay?
Professor?
Yeah.
So in practice, everything is serialized into strings.
In the proxy, no, it's not serialized to strings necessarily. You know, it's going over the wire, but I'm sure it's sending blocks of bytes. But you know, I've never looked hard at that wire protocol. There's a wire protocol that says here's how we're doing it. So you know, just like in our channels, you know, in SMA and OOD, we had a protocol, you know, and so, you know, and when we used WCF hid that protocol from us, but it was basically using HTTP under the covers. So HTTP is a message, has a bunch of strings as headers, and then a binary block at the end.
So so when the customized component do stuff, it's more of a communicating using the fx fy instead of calling function.
Well, it's calling fx and fy. If they're in the same apartment, it's directly calling those functions.
Oh, yeah.
But if they're in different apartments, now it's talking through a communication channel, and the proxy is breaking it down into the wire protocol, whatever it is, okay? I don't know what it is. I've read through, there's a Microsoft guy, I think he still works for Microsoft, his name is Don Box, and I met him once, and one of my former students was working with him and introduced me to him. And he didn't know quite what to make of me, and I didn't know quite what to make of him, but it was funny. But he wrote a book, you know, and he gets into some of those details, not all of them, but he gets into fewer of the details that he promises he will get into in the front of his book. But you know, that's the deal. So now, I have some comments here that I don't want you to worry about. Every new version of Visual Studio that comes out, they change stuff and code breaks. If you're using ATL, that's not so much true. But with raw C++ stuff, you tend to get a lot of breakage every time Visual Studio changes. Let me give you an example, if I can find them. So I didn't include them here. Let's go down to that directory. So issue 775 code improc. Maybe I didn't use them here. Okay, I can't show you here. I didn't use them here. But there's an example that we're going to look at next time that I'll try to remember and show you. I'm not using precompiled headers here. But COM, the wizards always give you precompiled headers. The default is to give you precompiled headers. And that gives you an std.afx.h and std.afx.cvp. And in that std.afx. Either H or CP, I've forgotten which, it defines a win version. And when Visual Studio updates, your win version is out of date and it'll fail to build. Okay, and you'll sit there, why is it failing to build, you know, pounding your head against the wall, and eventually, oh, you know. So when you build things with ATL kind of buffers you from that. But I think a week from today we'll build our first ATL component. Going to try to get there if we can. And that's really what what you're going to be mostly worried about. So I've got some notes about, problems you can run into, all kinds of crazy problems that happen from time to time. Here's this build issues. So old ATL, I guess this was just with ATL projects. Old ATL projects will probably fail to build. My old ATL projects will probably fail to build because the stdafx.h has out-of-date Windows version definitions. Now, here's what you need. Next time Visual Studio comes out, you'll need OX 07 or 08 or something. Okay, so the problem is that nobody knows to tell you that, and so you look and look and look. Why is this build? Why is this failing to build? Why is this failing to build? Why is this failing to build? Stack Overflow doesn't tell you. None of them know. Okay, so or if they know, they're not saying. But by looking at the definitions, following the compiler error back down through all the definitions is where I discovered this in the stdafx.h. So, but normally, we won't have those problems when we build ATL projects. Okay, so. Yeah, here's what I want to look at. I want to look at this virtual function pointer table, and then, but I'll answer your question before we do. Yeah.
How did you compile that .idf file? Because when I right-click it, I can't find an option to compile it.
Okay, so let me, unfortunately I just killed it, but let me pull it up.
Yeah, thank you. No thanks, I got that.
You got it?
Yeah, I got
you found it? Okay. So here's the virtual function pointer table. So if I had split, I did this. So what happens here is what we have in that improc underscore ex1 is we have query interface, and then we have fx and fy. But this diagram was predicated, suppose we broke it up. I want to show you for two different interfaces. What happens when we implement two different interfaces? So in this diagram, I'm implementing fx in one custom interface, fx in one custom interface, fy in another custom interface, and that says I have query interface add ref release fx, query interface add ref release fy, and in my so what's happening here is this is my so this is my CA object. If I don't have any data stored in it, I have a pointer to the IX virtual table, this guy. I have a pointer to this guy, okay, and I have the reference counts for each interface. Nowadays, in the old days, COM used to reference count the interfaces. Actually, this one doesn't, improc. But so for improc underscore 1, there'd only be one reference count. But in the old days, we used to, for some strange reason, we reference counted each interface. But the point is that if I have a series of interfaces, I'm pointing to different interfaces in my, so if I have one component that implements different interfaces, there's two different virtual function pointer table, two different pointers to virtual function tables. There's this table, and they happen to be concatenated together because it's all for one object. And if I've declared query interface first, that comes first, then fx. But it works like normal, virtual function pointer tables. So my fy is pointing to, so this is, I don't have a hierarchy, so I've only got one, I don't have several different derived classes that are, so, but, so each function is pointing to a slot in the code, so this is code space, and the virtual function pointer table is just pointing into those, so there's a pointer to query interface and so on. Now, what happens is, when I cast this, when I cast to IX of my object, so this is the virtual function pointer table, this is the virtual function, this is the object for CA, this is the virtual function pointer table for CA, and so when I static cast on CA to IX, that's pointing, that's setting this pointer, and it points to there. And when I static cast IY CA of this, okay, I'm pointing, so this always starts out at the top. So when I cast this to IX, IX is already at the top, so it doesn't move. Pointer doesn't move. When I cast to IY, that moves the pointer down to IY. All a cast does on those pointers is move it to the right slot in that pointer table. When I reinterpret cast to I unknown of this, it just goes to the top, okay, which points to I unknown. So, that's what those casts are doing in query interface, is just moving the pointers around in this virtual function pointer table. Okay, make sense?
Professor,
yeah.
In this case, for the reinterpret cast, what happens if we cast it to IY?
It just moves the pointer down to IY. So now it's typed as an IY object, and I can call. That allows me to call, so it's down here, so that allows me to call FY, but I can't call FX, okay, because it's pointing down to this table. So it doesn't know about FY. it doesn't know about fx. Okay, so when I cast it, it's just moving the pointer down here, which is bound to this part of the interface, and that allows me to use this query interface, this addref, this release, and this fy. And it's possible that these are the same functions, but they might not be. Okay.
So actually, I didn't get the difference between static cast and reinterpret even during the OD class.
So static cast on a pointer is simply moving that pointer to the appropriate place. I could certainly do a static cast to I unknown and get to the top of the table. Why is that a reinterpret cast? There's a reason for it, and I've forgotten what the reason is. I don't remember. Because I asked that same, why is this a reinterpret cast? Why does it have to be a reinterpret cast? And there is a reason for it, but I've forgotten. Okay.
We mostly use a reinterpret cast when something like when we are changing, like casting from one type to one other type.
Well, so what's going on? Reinterpret cast, what it's doing is saying, I don't care what type you think this is, treat it as this type. Don't change a bit. So reinterpret cast is saying, don't change anything. Static casts do allow for a change, but because we're static casting pointer, no change is going to happen. So in this case, I don't think there's going to be any difference between reinterpret cast and static cast.
It's on the
Same. I don't think there's going to be any difference in this example. I think I could change that to static cast and nothing would happen. Okay, we're about out of time. So what's going to happen, what I'd like you to do on Tuesday, for Tuesday we're going to do the following. We're going to look at there is an IDL presentation I'm going to go through. We already looked at this virtual function pointer table. We already looked at this code. We're going to look at this IDL presentation. These, we're not going to go through these. So beasters and safe arrays and variants are surprisingly complicated objects. They don't have to be that, they didn't have to be that complicated, but the designers of COM made them really complicated. There's a guy by the name of Bruce something or other who wrote really nice tutorial papers on them, and these are these tutorial papers. You don't have to know those details because the ATL wraps them in CCOM_beaster, CCOM_safe array, CCOM_ variant, and they're much easier to use. And that's what we're going to use. That's what I'm going to talk about. This is just saying, if you get into some situation, you know, where you really need to know those details, they're all here nicely. It's long, tedious to read, but nicely presented. So nice discussion of those. I'm going to talk a little bit about OLE automation types. What's happening is that when we build a proxy, we're building into that proxy information that comes from our IDL, the types that are going to be sent. There's a subset of types, smaller than all the types that COM allows, called OLE automation types. They're the types that the scripting automation interface understands, and there is a universal proxy for that. That proxy knows how to send all of those OLE automation types, and so if we use the OLE automation types, then we never have to build a proxy. We just automatically use the default OLE automation proxy. And the way we do this in the IDL, when we're defining the object, we say OLE automation. We qualify it with OLE automation, and now we don't need to build a proxy. ATL won't build a proxy, doesn't need it, just uses the universal one. So we'll talk about that a little bit, and if we have time, there's an interface